Before I start, I want to recap a bit how full-screen pixel shaders map to GPU units on NVIDIA GPUs, in particular the NVIDIA Turing architecture. And here is an example of an RTO denoiser that is implemented as full-screen pixel shader passes. This full-screen pixel shader, its instructions are getting executed on the SM, which is the streaming multiprocessor. And whenever it has to do an SRV or UAV memory access, this instruction goes to the L1 text unit, which is a level 1 cache and texture unit pipeline. And if the L1 text doesn't have the data in its cache, it sends a request to the L2 cache, which sits farther away from the SM, it's closer attached to the memory partitions. And if the L2 cache is missing its data in its cache, it sends a request to the VRAM. The VRAM is the GDDR video memory controller. And after the pixel shader is completed, it also completed a color, and that color gets returned to render target via the CROP unit, which is a color ROP unit. For each of these units, and for each key GPU unit on NVIDIA GPUs, we measure throughput percentage metrics. Those are measuring the percentage of the maximum theoretical throughput that a given unit is achieving, or if a unit contains multiple subunits, it's the maximum value across all of the subunits. And the throughput percentage metrics are also known as the speed of light percentage metrics or peak performance percentage metrics. And let's take the example of one of those RTO denoiser passes. We measure the throughput percentage metrics for each of those units, and we sort them in decreasing order. And the top one, the top value, is what we call the top limiter. And that is the unit that is mostly saturated. In this case, the top limiter is clearly the SM at 70%, and the next one after it is L1 text. So we know this workload here we picked is SM throughput limited, and removing work from one of the SM subunits will speed up. But recently we've released additional submetrics for the SM, and that's really cool because now you don't need to guess what subparts of the SM is limiting you. You can see it. You can see the throughput metrics per SM subpipes. And same method applies. We sort them in decreasing order. The top one is the maximum one, so that's the SM throughput. And the top one is the FMA pipe in this case. And the FMA pipe on Turing GPUs means well, it's executing FP32 add, mul, mads, ops, or other types of FP32 non-transcendental ops, and possibly also integer mul and mul and add. Ops can also be executed on FMA. So it tells you if you find what are the most commonly used such instructions in your shader and you remove them, you will very likely see a speed up. Now, how we get those throughput metrics? We've created this new way, this new tool. It's called GPU Trace Metrics Graph. It's part of the GPU Trace tool. It will be shipping soon. It's not out yet, this metrics graph feature. And it's using Turing hardware to capture hardware metrics over time using periodic sampling. And then this tool is displaying the metrics on graphs. So here you see this graph I've highlighted with the mouse cursor is the top throughput units. So for each of the GPU units, you can see the throughputs are sorted in decreasing order, and you can see that over time. But also, if you select a range, a time range in the tool, on the right side of the tool you see the summary, which are the average values for that range. And you can see these are the usual per workload metrics that we've exposed in the range profiler for a while. So you can see numbers, right? What are the average values? Here, the top SM, the top throughput unit is the SM FMA pipe, as I said, because I picked that workload. So why is it FMA throughput limited? It's a denoiser of pixel shader. So for us, it was a bit of a surprise the first time we saw that, because immediately we thought that's doing a heavy amount, more than 50 texture fetch per pixel. It's going to be texture or latency limited as usual, but no, it's not. It's FMA throughput first. And the reason for that FMA throughput limited case is every sample calculates a weight. The weight is extremely important for denoisers. The weight is based on world positions. For every UV coordinates that is getting fetched, that UV coordinate is transformed into a world position via 4x4 matrix multiply in this implementation. And 4x4 matrix multiply is performed, there is one such multiply for each texture sample, and there are like more than 50 texture samples in average over the screen. So that's adding up to a huge amount of FMA instructions. And we did this very simple experiment to verify that we are really FMA limited. Just take that instruction, remove the matrix multiply, and it doesn't affect the control flow of the program, because the branches and the texture coordinates, they don't depend on this world position. It's only affecting the look and the calculation of the weight. And doing that, we see a 23% gain on the GPU elapsed time of that single draw call here. That single workload, which is multiple draw calls inside. And the SM throughput percentage got down because the SM got less work to do. So it's less saturated, which is good. We wanted to do that. And the L1 text throughput got up by 20%. Also good. In the end, you can also see the SM and text units are more balanced. They are more balanced. They are 63 and 67, so this is also a good thing. Oh, yeah, and all these measurements, they were done on RTX 2080 using set stable power states to get deterministic results. We always set the power state to true in the DX12 apps when doing such profiling. But the GPU trace tool, in fact, it allows you to unlock clocks, but I don't do that because I want determinism. So now let's put what we've done here, into a method and a decision tree, in fact. So the first thing we look, before looking at the GPU side, is really, are we really fully GPU limited? Are we fully GPU bound? And the simple way to do that is opening up GPU trace and look at the GPU active graph and see if it tanks in certain places, if it goes down to 0, and in average, see if it's less than 95%. 95% is made up threshold, but if it's less than 95%, it means for more than 5% of that time, the GPU is fully empty. The graphics pipeline fully empty, and the copy engines are fully empty. The GPU is fully idle. So if you see this, you know there's a problem somewhere on the CPU side, or sending work to the GPU, and the GPU is not able to do anything. So this is the first thing to attack. If you see that, there is a tool that is very handy, and that is Nsight Systems. Nsight Systems, it has a very nice way to visualize on the timeline what are the frames that are bad, because you see them as red. And in this case, if you you just look at one frame, you can see even within that one frame, you see, okay, it's bad because it took longer than the adjacent frames, but you also see why it took long. And you see on the CPU threads where the threads got stuck on the timeline, and you also see the reasons for why they got stuck. In particular, you see if you got stuck by shader compilations on a critical path. This can happen, it happens very frequently on DX12 by creating pipeline state objects on the critical path. So if that happens, you see it as a red thing here. It's shown here on the screenshot. Maybe you can't see that, but you can also see if you're overcommitting video memory. If your application is allocating and if it's using more video memory than the operating system budget allows, there's a high chance that the operating system will swap out resources from the GPU during the frame execution and do bad things, like GPU active going to 0. So after you check that and you're in a good state where GPU active is great, so maybe 99 or 100%, you go and look at the GPU side and measure the top throughput metrics per GPU unit. And if the top one is greater than 80%, then you know that you are throughput limited by that unit. And first thing to do is remove work from that unit, and you will see a speed up. as we've seen, you can remove, if you FMA throughput limited, remove FMA pipe instructions, and you will see a speed up. If you, however, your top throughput percentage is lower than 60%, then you're latency limited by that unit. And what you need to do is reduce the latency of the unit because that unit latency is blocking also other units that depend on it. So and basically the other units, they are not able to hide the latency. That's a problem, right? The latency in itself is okay. You can say we don't know if it's a problem in itself, but here. Because it's a top throughput unit, we know it's a problem because there's no other unit is more utilized, more saturated. So we know we need to reduce the latency, or the other way to work around the problem is increase parallelism. So getting more things going on. For example, more warps active. To hide the latency of one warp, you get more warps active. That's a classic strategy to hide latency. Another strategy is using async queues. Right? Of course, getting more for example, again, more warps using async queues, async compute queues, but also maybe more copy work, more VRAM work using copy queues, getting more things going in flight on the VRAM unit in parallel with the other units. Okay, now I have a quick demo of the GPTrace tool live on that workload I started from. So this is the denoise.io workload in this frame that is doing RTO rendering, and it has this pattern. Right? It's 4 draw calls, and you can see the draw calls here. You can see each draw call is starting with it's about 0.2 or 0.3 milliseconds of top throughput unit being 33%. So during this time, the top throughput unit is 33, and then it goes up to 75, 78, 88. And so, why is that the case? When I saw that, I felt, wow, this is interesting. It must be, maybe the GPU is draining itself every draw call is draining itself or something like that. But there's a story behind that. So, yeah, you can see the tooltip is updated in real time as I move it, and every time it is updated, it's sorting the metrics in decreasing order. So if you just look at the top row of the tooltip, you see the top limiting unit. So very easy to see here. Anything that's purple at the top is SM limited. And then the yellow stuff is L1 text, which is right after it. So it's a very easy way to see, okay, I'm here over this whole thing, I'm SM throughput limited and then text limited. All right. But the problem is the gaps here. So, why are those gaps in the throughput percentage graphs? To debug them, we'll go to the next level, which is the SM occupancy. Because it's an SM limited workload, we want to understand why is that SM throughput going down. It's going down, all right, we need to debug this. Occupancy, we look at it, it's the active warps per cycle divided by the maximum number of warp slots that the SM can run, converted to a percentage, and we visualize it here on the second graph in GPUTrace. And the green stuff, the green pixels are the pixel warps, and the gray pixels are the opposite, which are the unused warp slots. And those, we break them down in 2 categories. We have the light gray and the dark gray. The light gray is unused warp slots on an SM that is doing nothing. It has no warp. Oh, by the way, the warps I'm talking about, they are the 32 threads executing in lockstep, right? It's 32, just to remind you, on NVIDIA. And so the light gray means it's really bad because these empty warp slots, they are happening on an SM that is doing nothing. So this SM is completely idle, and it's really, we want to avoid that situation in this case where we're SM throughput limited. The dark gray is an unused warp slot on an SM that has at least 1 warp active. So adding more warps to it, we don't know for sure if it's going to be beneficial because the SM scheduler would have to schedule it together with the other warps that were already there. But if an SM had no warps active, then the SM scheduler can surely schedule it because there was nothing, right? That's how we break down these 2 categories like that. So if you see light gray, really you want to attack that. You want to attack this. Dark gray here, We're not sure why is there an SM active that has unused warp slots. Why is the occupancy not getting greater here? But for this year GDC, we decided we want to expose more metrics to you guys to let you determine exactly what is the cause of this occupancy problem without having to experiment around and think, oh, maybe this, maybe register file, maybe this, maybe that. Here you look at the matrix and you pick the top one for the warp launch stall reasons, and the top one tells you the percentage of the cycles that the SM was unable to launch a warp due to a reason. And here the top one is the out of order warp completion reason. This means that because the pixel shaders have variable latency, because they are taking an early exit, in fact, well, not an early exit. There is a dynamic number of texture fetch that depends on the world position distance to the camera, and so this is a fully dynamic number of texture fetch. So the latency of the warps is completely dynamic, and some warps they exit very early, and those warps they cause problems due to the fact that pixel shaders that have out of order warp completion compared to their launch order, they will limit the occupancy because their output color will still consume some resource, and so this limits the occupancy. Solution is easy, converting that pixel shader to compute shader, because compute shaders don't have this constraint. They can complete in arbitrary order, and this will not limit occupancy. Now, coming back to this method, we were in the latency, we were first in the throughput limited case because we were 70%. So we said, all right, 70%, it's in the middle here between 60 and 80. Because we are in the middle, we are going to do the two branches. We start from the right side branch, we do the throughput limited branch, and we see, all right, FMA throughput. Let's try and remove some FMA instructions. We get a speed up. Okay, of course it was not correct, but you could work it out and make it, keep the transformation to some space, but have way less FMA instructions. The second branch on the left side we also took, because we are 70% throughput on the top unit. We said, all right, let's see how we can speed that up, and the latency limited branch tells us we can increase parallelism. So we did increase parallelism by looking at the occupancy limiters, and attacking the first occupancy limiter here is converting the compute shader to a pixel shader. And that gets the occupancy up. If you do it, it's just theoretical. Yeah, I haven't done the verification, but I know it would be beneficial for the occupancy part. Now, I've got some case studies, because I told you all about the method at this point, but let's see how it applies to many different workloads to get a sense that it actually really works. This is Metro Exodus, the DXR ray tracing acceleration structure updates. Those are running with a very low top unit throughput, VRAM at 3% of its maximum throughput. So we want to get that up. And one way to get it up, as I said at the beginning, is to use async queues, async compute queues in particular, in this case. We want to do that because especially the occupancy is really, really low. And you see all this light gray stuff, meaning that there are empty warp slots on idle SMs all over the place, all over time here. And we want to use async compute to pair that thing with another thing, overlap it in such a way that the occupancy will go up and the perf will be better. An independent workload here that the engine has overlapped with this is screen space pre-tracing. That's a ray marching step in screen space that's tracing a ray and intersecting with what's available in the gbuffer. If it finds a hit, it can use that hit information in the geometric tracing step to early out the actual geometric ray. So that can be an optimization, but also it's a quality improvement because this screen space marching is hitting the alpha test geometry better than what the geometric tracing does in Metro. It's a Metro thing, but it's anyway, it's SM limited first at 62% of the maximum throughput. And 62% is not that high. So it's also nice to overlap this guy because it wasn't that high to begin with. And the SSR workload is another workload that the engine has identified as independent. This one is way more throughput limited, and it's L2 throughput limited at 79%. Now, here's what we do. We take the union of all of those workloads that I said, the RTS builds, the SSR, the pre-trace, and we serialize them. We look at them on a single queue, and we look at them as one big thing. And they take, if you serialize them, they take 1.83 milliseconds. Now, we do the same experiment, except that we overlap them on 2 queues. So we have the direct queue does the BVH builds, the RTS builds in this case, and the I think compute queue does the rest. And you can see the delta. Delta is in GPU time is 41% gain here, and the throughput percentages per unit got up by 40%. So it's almost the same scaling factor. And the SM occupancy also got up. But as I said, we don't start from that. And you can see here, okay, occupancy got up, but it's not, as exactly the same scale factor. In fact, it may not be at all related. Occupancy may go up and performance may go down. So we always start from the throughput percentage metrics. Now, another case study, real quick, is overlapping a sync compute with shadow maps, and that's a very classic example. Because shadow maps are independent, they're not from the primary view. You can basically overlap anything that's just doing the primary camera rendering with it, so it's very handy. And in this case, this is Battlefield 5, and it has this execute command list with the HBO, SSR, and light culling in it. And it's as a whole, it's VRAM throughput limited with a poor VRAM throughput percentage. But there's also shadow maps that is L1 text limited at 38%, so also not so high. But the engine is overlapping these two things, and after overlapping them, there's a 14% gain. And the throughputs, they go up by 10% or 19%. And the SM occupancy goes up also. So yeah, this is just a classic example, the shadow map overlap. Now, here's a bad pairing example. This is Blur compute shader, and it has the top throughput units VRAM at 61%, and then L1 text. And you may think, well, VRAM 61% is not so high. I would like to overlap that and get it up. There's an independent workload in this frame, that's the water simulation, and also has a low top throughput, and VRAM also, and a gbuffer field, which is also VRAM limited. And so after overlapping all these things, we see that overall the perf has gone down, 0.96x loss in performance. And the VRAM throughput has gone up, but the other throughputs have gone down. And most interestingly, the L2 read hit rate, it went from 52 to 44. So what happened is that because all of those workloads, they were VRAM latency limited, and in fact, they happen to be using the L2 in thrashing the L2. Putting them together thrashes even more the L2 cache. And overall, increases the latency of VRAM. So overall, everything gets lower. And let's see exactly. So the first one had a 29% L2 read hit rate, the Blur compute shader. We overlapped that with the water simulation, which had a 44% L2 hit rate. And the gbuffer also had a better but not so great 61% load hit rate. So the bottom line is it's a bad idea in general to overlap VRAM latency limited workloads. Now I've added a new node in the decision tree here. So if we are in the latency limited case on the left, with the top throughput less than 60, we check the top unit. If it's VRAM, we are VRAM latency limited. And in this special case, the thing to do is reducing VRAM accesses. This is it. This is simpler. And you can do that by increasing the hit rates of the L1 or L2, or by reducing the amount of VRAM accesses themselves by reducing the amount of bytes that is getting fetched, for example, using tighter texture formats, just reducing the amount of traffic bytes that get requested from VRAM. Here's an example of a VRAM denoiser, VRAM limited denoiser, compute shader. It's from Battlefield 5, and it's at 2K with DXR. And the top throughput units are, again, our familiar VRAM at 57%. And you can see here in the tool, in highlighting a feature of the tool, which is on the right side, you can click on metrics, and then you can search for something in this text field, and it will show you all the metrics that contain that string. In this case, we have the VRAM read and VRAM write subunits of the VRAM throughput, so we can see, in this case, we are VRAM read throughput limited. That's useful information. And we can also search for L2, and we see here, okay, we are L2 read hit rate limited for that entire workload, the denoiser. The 32% is really bad again. Same signature as before, right? VRAM latency, bad L2 read hit rate. And now we go one step further and look at the SM warp stall reasons. They tell us the percentage of the active warps that are stalled due to a reason. And over time, over this entire workload, 77% of the active warps, they are stuck because they're waiting on a texture instruction to complete, to come back. This is a huge number. This is like they are all these active warps, but 77 of them, they're waiting on texture instruction to come back. And we can put everything together because we have this bad L2 read hit rate at 32%. We know that the latency of each of the texture fetch is going to be very high. If it goes to VRAM, it's very high. And the L1 hit rate is not that great either. It's also 55. So that explains why it's VRAM limited, because there are so many misses in L1 and L2. And also explains the latency is so big. Text latency limited is the signature here. So this is a compute shader, I said it. It's 8x8 thread groups, and they are launched in this way. It's the raw, by default, if you launch a 2D compute shader, the launches are in raw major order from left to right. So the first one is here, the second one, the next launched thread group is on the right of it, and then it goes like that. It fills in the first row from left to right, and then it goes to the second row. And the problem with doing this raw major launch order is that the distance between the last thread group on one row and the first thread group on the next row can be very high, especially as the resolution of the input texture, the 2D image gets bigger. The distance gets very high. The problem is that those thread groups that are getting launched here, they get assigned to different SMs on the GPU, and they all work together simultaneously. And they're all accessing the L2 cache lines simultaneously. And the resulting working set that needs to be stored in L2 for everything to work simultaneously gets bigger and bigger as the distance between these two guys gets bigger and bigger. So eventually the working set size gets bigger than what L2 can handle, and it causes this terrible L2 thrashing. So the solutions are to remap the thread group IDs. And here is what we've done successfully, and that's tiling. Instead of launching them in the blue order, the raw linear order, the raw major order, we launch them in a tile manner. So we start from the first left side, and we launch 16 thread groups, in the first tile. And then we go to the second row of that tile, and we fill in the first tile, which is 16 thread group wide. And then we go to the second tile. And this lets us keep under control the distance. I talked about the distance between the last thread group of one row and the next thread group on the other row. We keep it, this is a parameter, right? And in this case, we picked n equals 16. It just happened to work, but it's very easy to experiment and pick some value that works. And it's a small amount of code, of instructions to add at the very beginning of the compute shader. It's just doing this remapping of the thread groups. That's all. With this, we got a 47% speed up on this denoiser compute shader. It's an actual real denoiser from this Battlefield 5 2K example. And the VRAM throughput percentage got down, which really we wanted to do that, right? By about half, and SM and SM throughput got up, and it got up by about almost the same as the performance increase, and the L2 read hit rate also got up by a huge amount. Now it's 86%, which is really, really great for L2 hit rate. Yeah. However, yeah, the long scoreboard, warp stall reason, which is indicating that there's lots of warps waiting on texture dependencies. Okay, it got down, but it's still big. And so it could be the next thing to attack. Then, right? You solve this, now next level, we want this down. So. But anyway, we're here on the decision tree. We were VRAM limited, VRAM latency limited, and we fixed the main issue by increasing the L2 hit rate. And that was done by just reordering the thread IDs. Another example now that is not VRAM limited is the lighting compute shader, a lighting compute shader using shared mem. It has a top throughput unit, SMA FMA pipe, SMFMA, and it has a lot of unused warp slots with active SMs, 51%. And we can look at the warp launch stall reasons I mentioned before to see the reason why this occupancy is so bad, right? 51% of the warp slots are unused, so very bad occupancy. And the top reason is this shared mem allocation reason, 93%. So during 93% of the elapsed cycles here, the SMs are not able to launch warps because there is not enough size, not enough resources available for the shared memory part of the compute shader. The shared memory size is too big. And the other reason why we are SM latency limited here is the long scoreboard again. The texture latency is big. It's 42% warp issue stall on long scoreboard. So those two reasons are very powerful for us because with these two numbers, I know two ways to attack this. I know one way, reduce my shared memory size. I would get the shared memory allocation down and I will increase my occupancy. My second way, which is orthogonal, both are good, is reduce my long scoreboard, which is reduce the text dependency. So I will show you how we actually fix this one by reducing the shared memory size. All right. The initial shared memory layout is, in this compute shader, is storing light data. And it's storing all of the attributes of the light data that are used for lighting here directly in shared mem. But really, this light data is coming from a constant buffer. And it's a shading path. So it's accessing this light data in a uniform way where every thread is fetching the same light data at the same time in a lockstep. So what we've done is, instead of storing the light data in the shared mem, we store an index to the light data. We store the index to the light data. And whenever we actually need to shade that light, that's the place where we fetch the constant buffer. And because these are uniform, there's very, very good performance for constant buffer loads at that time. By doing that, so we effectively reduced the shared memory size. We were here in the red dot, and this is the CUDA occupancy calculator for Turing. It's available in the CUDA SDK. We're here, we reduced the shared memory size up to a point where it was no longer limiting occupancy at all. We are at maximum 32 warps on Turing, it's maximum 32. You can see the effect here. We got a 38% speed up by doing this shared memory size reduction and moving constant buffer, shared mem to constant buffer loads, and increasing SM throughput, and also we are no longer limited by shared mem allocations. This goes down to 0, so we've got infinite ratio here for the warp launch stall reason on shared mem. And that's really nice. So now we can go really fully to the next step. We've attacked the first one. We can really fully focus on the long scoreboard. So you can see it's still there, right? It's 38%. But yeah, we're here, latency limited, and we've increased performance by increasing parallelism, by increasing occupancy, by reducing the occupancy limiters. And my final case study now is thread divergence limited dispatch trace in Battlefield 5. This is this frame from Battlefield 5 in 1080p DXR Ultra. And it has this top throughput percentage signature, L2 at 24% of its max. And it's pretty low, right? So we really want to do something here. But what we've noticed is that, okay, L2 is the first one, but why is it so low? we go back the dependency chain, right? L2 is called from L1, which is called from the SM. So we check, go back to the SM and look back and notice this active thread per instruction executed percentage is really low. And that indicates that there are empty threads in the warps, just empty lanes in there, that for some reason we are not able to pack enough active threads in there from the beginning, or more likely that there's a high divergence in execution between the threads. And it's 29%, that's so low. So we want to do something, and the way to fix that for dispatch race calls is simply to realize that each of the threads is one ray, and if they hit different materials, they will have to essentially pick different branch bodies, right? So as they hit, depending on what material got hit, they will execute some different portion of the shader based on a sort of branch. So to reduce the divergence, one way is to reduce the number of hit shader permutations. The number of hit shaders are getting hit, so they more are going to execute the same bodies of code. Reducing the number of hit shaders. But there's another metric that's interesting at the SM level. As usual, we can look at we are latency limited, right? So we can look at the warp issue stalled reasons. And there's this one that pops out. Again, the approach is always the same. You sort the reasons by decreasing order. Look at the top one. In this case, the top one is no instruction at 70%. So that means that 70% of the active warps are stuck over time, over this dispatch race. They are stuck because they are waiting for their instruction to come from the instruction cache. And to fix that, one solution is to reduce instruction count in the hit shaders overall. Basically simplify the material shaders used in this dispatch race is one way to attack that. So if there are less instructions in each of the bodies of code that are getting hit, that are getting executed, there will be less thrashing of the instruction caches, and this will go down. Now there's a third way that I have to say I discovered a bit by accident as I was playing around, and it actually is a third way that is playing with the opaque flag. The opaque flag, it's something that you can set in the blast geometry description, or it can be overridden in the instance flags as well, in the top level acceleration structure, or it can also be overridden in the flags of the actual trace ray call. Anyway, this flag says that a given triangle, a given set of triangles is fully opaque. That means that if a ray hits that, we know that the ray is ending here. It will not go through and have to spawn other rays. And let's see how this flag interacts with everything. So this is the original frame where it's taking 1.13 milliseconds. And now a frame where I force the opaque flag for all blast geometries. All bottom level acceleration structure geometries have the opaque flag now. And you can see the difference is this sort of lack of fire reflections on the weapon, right? And the result of that experiment is that we got a 95% speed up. About 2x. Yeah. So 2x gain, right? 1.95x gain for something as simple as forcing a flag, that's surprising. In fact, this happens because look at this row here. The SM instructions executed per warp got down from 725 to 425, almost half. And the divergence problem also got better. The SM active threads per instruction executed got up from 29 to 40. There was a 40% increase here. This happened, in fact, because as the rays, they hit the opaque triangles, they don't go behind them. And so they don't have to evaluate the materials that are behind those opaque triangles. And it's a very nice side effect. So this is way more efficient as a whole because one ray doesn't evaluate as many hit shaders. So the speed up here, it doesn't come from an increase in top throughput percentage. It comes from a direct decrease of the latency of the warps. The latency from the beginning of one warp to the end of that warp running on the SMs. So we're here, we are in the L2 top throughput latency limited case, and we increase the perf by reducing latency. It just happened to not be the latency of the L2 directly, but the latency of the SM, and that's okay. And we did that by reducing instructions executed by just setting that flag. Of course, this is changing the output image, so this is not like saying this is the solved problem, but if you know that opaque flag is affecting so much the perf, then you can definitely be more aggressive setting it. In this frame, there are so many trees that have the that flag not set on the tree leaves, and it's questionable if it's really needed. All right, so to sum up the NVIDIA tools that we have available for getting those hardware metrics, there are two. There's the range profiler, which we have been supported for a while, and that now supports Vulkan, DX11, DX12 as well. And there's GPU Trace, the matrix graphs, which is DX12 only so far, and Turing and beyond only. But GPU Trace has advantages because it can plot things on graphs. So you can see things like I've shown where you have weird patterns and unexpected changes within one workload. And also, very importantly, it works with async queues. Whereas the range profiler, if you have async queues, it will serialize all of the queues into the direct queue for isolating the workload that you want. So it doesn't exactly give you the same answer. And the P3 method, well, it's called P3 because it's peak performance percentage. Or throughput percentage, right? And that method, it works. We use it to attack any GPU workload. We don't start with knowing what the workload is. We don't need to start and know what the algorithm is within that. And it's very powerful because then you understand your limiting GPU units and exactly the characteristics of why they are limited. And then if you walk backwards to the algorithm, then you can really solve the puzzle really much more efficiently if you have everything coming together. So we don't start from the occupancy. We start from the throughput metrics. This is very important because, as I've shown, starting from the occupancy may make you want to pair something with something else just to get the occupancy up because you feel that's important, you believe that's important. But it may not be a speed up, it may actually hurt because if there is a VRAM latency limited, increasing occupancy for that one is not a good idea because you will be even more VRAM latency limited, more warps wanting to access the VRAM. So, async compute rule of thumb, do not overlap two VRAM latency limited workloads. I think that's a good idea. And we will keep updating our blog post. We've had this blog post for a while, and as we learn new things, we tune it, we improve it. So the continuation of this talk will be on the web with the blog post. Now it's time for questions. Please. Come to the mic.
In all the talk, you focus very much on the SMs and the reasons that they can stall, but you didn't touch at all on the RT core parts of the Turing GPU. So presumably they can have the same sorts of problems as L1 hit percentage, L2 bandwidth limited. Does Nsight have any insights, metrics into why the RT cores themselves can stall? Because you could very easily have a dispatch raise core where the hit shader just returns red, and so the hit shader, the SMs are going to be doing essentially very little. What insight can you give me into what the RT cores are doing?
So first insight is there is a pro version of GPU Trace that exposes RT core metrics. And second insight is having worked with those metrics a lot didn't help to do anything better than what I've shown you for the dispatch race I've shown. And in many dispatch race cases, if you look at the internal RT core metrics, it's nothing actionable to you. That's the other thing, right? It's if you have a lot of instructions in your shader, in your hit shader, well, you can do something about that. That's your shader, right? But if it's the RT core, there's some stuff you can do. If your BVH structure, if you have too many instances, for example, that can be a problem, right? But it's a secondary level of problem, to be honest. Usually, we see the problems are on the hit shaders and they're not so much on the traversal efficiency itself. That's what I've noticed. So that's why I feel okay to, in this we are not ready to show the RT core metrics publicly, but we have the pro version that does that. If you really want to go into that, you can do. But if you don't have the metrics, you can still do a good job because you've got all these SM level metrics and the top level metrics for everything else than the RT core.
Okay.
Yeah.
Hi. When will we update these features? When will it be updated?
Right. I said it's coming soon, right?
Coming soon?
Yeah.
Okay. Thanks.
Okay. No kidding. It's probably we want to do that within 1 month or something like that. So it was not exactly completely ready. So that's what I've shown is preview. Everything is preview, right? We may change a bit the names of the few metrics and stuff, but it will be overall the same tool. Yeah.
Is there an Nsight tool that shows you the disassembly of a shader and if there are spill fills and which source lines they may map to?
Yeah. There is a pro version of Nsight that can show you that, and we're working on a shader profiler within that, so you can see if you have those warp stall reasons that I have shown for the workload or over time, you can then look in the shader instructions, low-level instructions, right, and see what instruction has what stall reason. And you can see the percentage of stall per instruction at that level. Yeah, but it's again not quite ready, and we're working on finishing it up for DXR because dispatch rays are very complex things, right? And so we are finishing that up, but it's going to be for pro versions of Nsight. So for pro versions, you have to talk to us. Please talk to us and ask us just access. We just need to give you an account.
Thank you.
Hi. How is the opaque flag different than just calling accept hit and end search in your any hit shader?
Sorry, I didn't catch the second part. Better than what? Or different than what?
Different than calling accept hit and end search in your any hit shader. So
it's different because there is no hit shader executed at the traversal part. So it's really helping the RT core to traverse better. That's why it's used by the RT core to traverse the BVH structure. And if you have a closest hit case where you want a closest hit, it will use that opaque flag to discard things that are in the back at the traversal time, without even having to execute any hit shaders. It just knows that that's fully opaque triangle. It doesn't even traverse in the back, right?
okay, thank you.
Yeah.
Hi, thanks for the talk. Do you guys do anything to surface like tensor core occupancy?
Yeah. There's a tensor core metric. I didn't include it because I thought it's going to make my slides too busy, but we have it. It's actually public. Yeah. So tensor core related, I just clarify that at the moment there is no direct way for developers to program the tensor cores. Publicly, there's no way, and the only way we think that they are useful as of today is for DLSS. So that's why also it was a less important thing to include. Yeah. Thank you.
Thank you.